This large-scale fluid system looks a lot like the first example. In fact, the only difference between this and the previous example is where the inlet flow is located. In the first example, it was going into tank 2, and here it's going into tank 1. So slightly different system, and we're going to be looking for a different transfer function. Here, we are going to be looking for Q out over Qi as our one desired transfer function. Making its diagram will look largely the same as what we saw in example 1. Again, the difference is going to be the placement of that current source, that Qi. So that's where I'm going to start with my current source, and that's going to be going now into tank 1. And that is going to have a current of Qi. Once we get into tank number 1, there'll be two things that can happen. We can have some of that flow, some of that fluid going to filling our tank. So that's going to go across this capacitor. And some of it can go into tank 2. So it's going to go across that valve R1 as it makes its way to tank 2. Now, in tank 2, there are three things that can happen. Well, one of them we've already accounted for is that fluid can go between tank 1 and tank 2. Fluid can also go to filling tank 2, so it can go across this capacitor C2, and some of it can go through the valve, the R2 resistance valve, out into the environment. And that's going to have a flow of QO. So let's mark some of these here. So QO is going out into the environment. We are told to use Q1. Here we're going left to right in our assumption of its direction. And then I will have to add a Q2 here for the flow that is going to filling tank number 2. And actually I'll need a flow here. I'll call this Q3 because now we do have to have that branch at tank 1. Some of the flow goes to filling the tank. Some of it goes to moving between tank 1 and tank 2. So the flows are here. Going to the environment is going to be treated like going to ground, and also the bottoms of tanks are going to be connected to ground or 0 voltage. So now I can put in my nodal voltages. So those are all 0, they're all connected to ground, and I have those two other nodes left. Well, those are going to be the pressures in the respective tanks, P2 and P1. And that's our complete diagram, very similar construction to what we saw in the first version of this example. My nodes are labeled with voltages or pressures, and all of my currents are labeled, or my volumetric flows are labeled as well. So what are we seeing as a difference? Well, again, the placement of the current source, and I actually have a third flow, Q3 here, that I did not have in the first example. But otherwise, it looks very similar to what we saw. So let's use our diagram and develop our equations to get QO over QI ultimately. So equation-wise, let's see, we can do a KCL equation. I like to start with those. And I'm going to start by doing the KCL at that P1 node. So going in, I will have QI. And as it's drawn, coming out, I'll have Q1 and I will have Q3. So outputs so far Q1, Q3, and our input of Qi is in an equation. And again, I'll mark that because I need the transfer function to have it. As my input, I only have one input here, and at least it does appear in an equation. Unlike the first example, I can do actually a second KCL equation. I'm going to do that at the P2 node. And we'll look at all of the voltages, all the currents going in. So here going in, I will have Q1, and then going out, I will have Q2 and QO. So Q1, that was already there. Q2, QO are new. And in this example, the transfer function I want is QO over QI. So that now appears, but I have 4 outputs, only 2 equations so far. Really, I'm out of KCLs to use, so let's look at some voltage drops. As in the first example, I can probably do this with fewer equations than I'm going to present. But I will do just a thorough job of having the equations and the outputs that we might be interested in tracking for this example. So let's go between P2 and the ground in that lower right. So we're going to go with the flow Q out. So 0 minus P2 will be the voltage drop across, well, we just go over one resistor R2. So minus R2 Q out. And that has added here, actually another output, P2, and a third equation. So I have 5 outputs now. Let's look at another voltage drop, node-to-node voltage drop. So let's pick a different pair. I'll stick with P2 as my starting point, but now go down to the middle. So my end point minus my start point of voltages or pressures is going to have a pressure drop. I'm going with the direction of Q2, so minus 1 over C2S Q2. Q2 already appears, P2 already appears, so I've not added another output, but I still need more equations. Let's look at P1 to P2. So between those two nodes, again, I'll go with the direction of Q1, so my end point is P2, my start point is P1, which unfortunately has added a 6th output, and I'm going across a resistor R1, so a voltage drop, a negative R1 Q1. Q1 already appears here. I have 6 outputs, so I need at least one more equation, and I still have one more node-to-node voltage drop I haven't used yet. I haven't gone from P1 down to the lower left. So going with Q3, 0 minus P1 equals the voltage drop across a capacitor, negative C1S times Q3 is the current. So looking at our collection of equations, I had 2 KCL equations in this case. I had 4 node-to-node voltage drops. Double checking my outputs, I have 6 of them, including the one I want for my transfer function. 1 input, the one I want for my transfer function. I have the 6 equations, 6 outputs. So once again, this will become a solvable system. We have 6 equations instead of 5, like in the first example. Once again, I am going to use Mathematica. I'm not going to try to solve this by hand. I will clean it up a little bit. I'll get rid of these zeros that were here just so we remembered our endpoints. And now it's just a little bit less to put in, a little bit cleaner to look at. So we'll dive into Mathematica to get our desired transfer function now. Now I can put in my equations from the first KCL. I have this Qi is Q1 and plus Q3. And again, I like to note here, this is coming from KCL, I'll call it KCL1, since I do have 2 in this case. Second equation, let's pull this down a little bit, is going to be Q1 is Q2 plus QO. Again, coming from KCL, my second KCL. Third equation, negative P2 equals negative R2 QO. Q4, another node-to-node voltage drop, so EQ4 equals negative P2, double equals, and I'll put in my fraction here, negative out in front in this case, 1 over C2S times a Q2. My fifth equation, P2 minus P1, is negative R1 Q1, and make sure there's a space there. And I had that sixth equation in this example, a negative P1 equals, and again, I don't feel like typing all of this again, so I'll just copy it down here and change it as needed, C1, and this is actually Q3 now. Negative P1, 1 over C1S, Q3. All right, so just double checking our equations, and everything seems to look okay. So I'll run this, I'll define my equations, And now I'm going to be ready to solve, and I want to take a look at what are my 6 outputs here, make sure that those are going to be included when I do my solve. So I'll just make sure I can see those at the same time in my solve step. So solve 6 equations, EQ2, 3, 4, 5, and 6, for Q1, Q3, Q2, QO, P2, and P1. 6 equations, 6 outputs, so I will let it solve them. Everything, it looks like it was able to do it. All right, so 6 potential transfer functions are now listed. But again, in this example, what was I interested in? I wanted the Q out over Q in. So that's the only one I need for this example. So my transfer function is going to be the QO one, is all I care about for this. So let me take that and I'll paste it down. Remember, the transfer function is Q out divided by Qi, so I will divide both sides by Qi, leaving the numerator as 1. That's my transfer function. Now I want to clean it up. So I'll put in my collect terms, and now I have the nice transfer function as put here. And if we look at it, we'll do the comparison again when we write it down. The denominator is actually exactly the same as what we saw in example number 1. That has not changed. The numerator, though, is different. The basic setup of the system is the same. It's just where that input was located is what changed. So I guess it shouldn't be too surprising the denominator matches, as it's more or less the same system. But let's get this written down and get our final transfer function then. Now let's write our transfer function. Q out over Q in is the one that we desired. And using our Mathematica, well, this one's nice, it's just 1 on top. And putting it on the right order on the bottom, C1, C2, R1, R2, S squared, plus C1, R1, C1, R2, C2, R2, S plus 1. And that is our one desired transfer function in this system, the output flow over the input flow. So going back briefly, we have basically the same system we saw in the previous example. So we need to take our fluid system and turn it into a diagram, a circuit diagram. So the only difference is we now have our current source going into P1 rather than going into the P2 from example number 1. Well, what that changed was the diagram just a little bit, but it did change our equations, as now we have 2 KCLs to use at P1 and P2, since now P1 has multiple directions the current can split, and P2 does as well. So 2 KCL equations. We actually added a 6th equation because we also added a 6th output. This Q3 was not present in the first example, but it is now, just because of the change of location of that current source. So we developed 6 equations, 2 from KCL, 4 from node-to-node voltage drops, for our 6 outputs, including the QO that we were interested in for our transfer function, and then the one input QI. I took the 6 equations, this solvable system, put it into Mathematica, and let it do the algebra for us to get our final transfer function of Q out over Qi.